Soil and groundwater contamination is a worldwide problem. In the past 30 years, DOE has been leading the technology development to clean up such contamination and also the simulation capabilities to assess the future risks of these sites. Recently, there are concerns about the impact of changing climate, a shift in the water cycle, and extreme rain events potentially remobilizing residual contaminants. It is a challenging task for site managers to take actions since there are significant uncertainties in both climate projections and in groundwater systems. The ability to assess the future groundwater contamination under climate change will be really powerful for protecting our water resources. We thank our partners, faculty, and researchers for pioneering this work.
Hello, everyone. We are the Digital Twin Environmental Remediation team. Today, we're going to share our effort on the most important human need, water. So water safety is critical to human health. 50% of our drinking water comes from a hidden world beneath the Earth's surface, which is called groundwater. With the climate change, we often think about if we have enough water to use. We might overlook the toxic contamination in the water. Here is one contamination site near the residential area. Contaminants would be from the industrial or agricultural activities or Superfund's landfill sites, and any extreme precipitation from the climate change might push the toxic contaminants towards the groundwater and drinking wells. We actually have thousands of contamination sites in the US, and 2 million people are near those sites, especially disadvantaged or minority communities. Wouldn't it be nice to ensure good quality for the future generation? However, it's a difficult task for site managers to decide whether and how they should take actions to protect our groundwater. If they have a tool like these multiple slide bars, then they can visualize the spatial temporal variations of the contaminants level, what we also call the plume, for the next 10 years, 30 years, with various climate projections that could be wet or dry with uncertain subsurface properties. Then they can make smart decisions before something happens. For example, those contaminants reach to the drinking well. Then in our digital twin project, we leverage the machine learning to help us deliver rapid plume evaluations under climate uncertainty. We have flow and transport physics simulations to provide a training set. And the biggest strength for our approach is that we can incorporate all uncertain climate scenarios from the global climate models and uncertain soil and subsurface properties from the local groundwater sites. We are integrating global climate and local groundwater models, so we call our digital twin multi-scale digital twin. This multi-scale digital twin would enable a fast plume prediction, predicting the spatial temporal plume variations with realistic climate projections. Now let's see our great FDL team. Ileana and Takuya worked on the climate data analysis and clustering. Aurelia and I, Lijing, worked on the plume emulator. We also got very strong support from our beloved faculty team. Now let's go back to a more in-depth view of how we're going to tackle this problem. We perform a detailed climate analysis, classifying the entire US into a set of representative climate regions using unsupervised learning, so that we can quickly access the climate data for any target location. This analysis provides realistic historical and future inputs, including variables like precipitation, water goes in, and evapotranspiration, water goes out. We also use uncertain subsurface parameters like the permeability, which indicates how fast the water can travel through the subsurface. With this, we developed a machine learning emulator capable of producing realistic contaminants plume predictions through time. Behind the scenes, this emulator solves partial differential equations faster, which is suitable when working with complex flow and reactive transport. Now let's see our actual predictions. I'm going to hand this over to my teammates, Aurelian.
Thank you, Lijing. So to demonstrate the capability of our model, let's take a look at an example. We're going to change one input parameter, the recharge, while keeping the rest of the inputs static, and see how our plume prediction changes. Recharge is the amount of water that gets into the soil and reaches the groundwater. Typically, increasing the recharge means that there is more water present in a system and therefore remobilizes contaminants or causes dilution. Let's start with a very low recharge value. So with this value, the contaminant plume looks like this. Now let's increase the recharge by 6 times and see what the model predicts. We can notice from the difference between the two predictions that in certain regions, the concentration is higher, shown in red, while in other areas, mainly on the boundary, the concentration is lower, shown in blue. If we increase the recharge even further, this trend may look the same, but upon closer observation, the concentration increases are not as widespread and are more localized in certain areas. This just goes to show how complex these physical systems can be, but mainly highlights how technologies powered by artificial intelligence can differentiate between nuanced relationships and effectively make predictions. We tested our models on unseen data and were blown away by the results. Here is a randomly selected sample where we predict our contaminant concentration, give it some input, and compare the results to reality. Visually, the prediction is nearly identical to the ground truth. Only when we plot the differences between the two can we notice the tiny errors made by our model. As a matter of fact, the majority of the testing cases gave us accurate predictions. Further tweakings and optimization methods could be applied, but as of right now, our model gives us the correct overall trend of contaminant flow and transport. We successfully developed a machine learning-based multi-scale digital twin. We reduced the dimensionality of climate models into representative regions, while also minimizing the computational burden of contaminant transport simulations in groundwater by creating an emulator. This emulator supports rapid decision-making for site managers and can evaluate spatial temporal contaminant variations instantly. We also developed an unsupervised approach to reduce the dimensionality of the vast historical and projected climate data. The lower dimensional unique climate patterns helped us quantify reliable future recharge rate projections immediately without having to download large amounts of climate data. We think this is a great starting point. Our future goal is to make this tool available at any site globally. To accomplish this, we need a more generalized, location-agnostic physical simulations and unique climate patterns globally. We are also going to build a user interface for site managers and local agencies. With the uncertainties of climate change, the flow of toxic chemicals in groundwater needs to be closely examined to ensure safe drinking water. Thank you everyone for listening to our presentation. We really hope you enjoyed. Now I'll hand it back to the MCs.